Welcome, welcome, welcome to Chemistry with Miss Lisa. We're going to be using this book. I'll write the ISBN in the description. This class is primarily designed for homeschoolers. I am a science and math teacher. I've been doing this for years, decades. We won't talk about how many. And I am making these videos primarily to bless the homeschool community, and so that the homeschool kids that I've been tutoring can continue on in their high school science, because I've gone back to teaching public school. And but if you like the way I explain things, then anybody can watch these videos and learn a little bit more chemistry. My background, my degree is in science. It's not an education degree. I went back and added that later. And so my first love of all the sciences that I've done is chemistry. I started off as a chemistry major years ago. I ended up kind of tweaking it more to a biochem major, but chemistry is just what I love to teach. Don't tell the other video section, but I really enjoy teaching chemistry more than biology. I like biology, but I really love math, and I also have math videotapes. And chemistry is a little more mathy, which makes total sense, right? It makes sense that there is not much math in biology because it's studying organisms. But anyway, sorry about my voice. This is late summer, and late summer the ragweed starts blooming, and my voice does this every year. It doesn't hurt, but it just sounds terrible. So terrible for you. You might go, I cannot listen to that woman. I'm going to cut this off, but it should get better soon. And I did take some Claritin, so maybe I'll start getting better. All right, so this is chemistry. I'm going to do each chapter of this book in each week, and there's only about 26 of them, but some of these chapters you will probably need to take more than 1 week on. We're going to have labs, and I know you're at home. You won't have the same experience as if we had been face-to-face and could do a little bit more chemically labs, but you can still do labs and still learn from labs and it being hands-on. There are activities in your book that don't need a lot of equipment, and then I'll add some stuff to that. How the class is going to work is that it will have homework in the description each week. I will tell you what I want you to do. You don't have to have the teacher's edition, but you could have it, and that would be a nice resource if you want to buy it. This really is an older edition. You probably can find the teacher's edition pretty cheap. The places to look are eBay, Amazon, and I think it's Alibris. I always say Alberus, but it's Alibris. And those are places where you can find the teacher's edition. Also, though, there is a free Facebook group, and but instead of being Miss Lisa, because my son set up the YouTube channel and my friend set up the Facebook group, the Facebook group says Mrs. Lisa, MRS Lisa. But on the Facebook group, moms can join, and there are tests and answers. So it's free. More resources there, and I mean, I don't know how many years this is going to be on video, and I don't know if my friend will continue to do this forever. But right now, there's a Facebook group that has tests and answers, so you kind of don't have to have the teacher's edition. The other thing, like everybody else on YouTube, I say like, share, subscribe. The reason why is I used to do these videos on Facebook. I would record our classes and stream them directly on Facebook Live, and they would just post instantly. The problem is when I did these classes, I had kids in them, and I can't, and Facebook makes it hard to go show them again. So I'm re-recording all the chapters, no kids, just me, on YouTube. So that's really nice. People will be able to find it easily. I'll be able to organize it. But the problem is because I have less than 1,000 subscribers, I have to record the video and then upload it instead of being able to just upload instantly like when I would do Facebook Live. So it will be easier. So I keep saying, but I have to have 1,000 subscribers. And my kids just keep saying, Mom, it's not going to happen. But I can dream, right? So especially because this is a great free resource for the homeschool community. People can have a high school science class with a lab component in chemistry, physics, biology, physical science, pre-algebra, which is actually a middle school class, an 8th grade class, algebra 1, algebra 2, and geometry. So those 8 classes are available for free. The books are older editions, so they're pretty cheap, and there are tests and answers free on Facebook. So it's a really great free resource. Hopefully you will agree with me, for the homeschool community who need high school, some help with high school. So it's a little bit cheaper than, joining in at some other class. A whole lot cheaper. You just got to buy the book. All right, so we're going to start with chapter 1. Now, what do you need for this class? And of course, mine is not here. You need a scientific calculator. The cheapest one that I approve of is the TI-30. Sometimes it's TI-30X scientific. They're about $8 to $15 at Walmart, Target, all of those places. And if they're on sale, sometimes you can find them for like $8. Not on sale, sometimes they're as much as $15. But you can think of them, they're probably going to be about $12. And that will get you through this class just fine. No problems. The thing is, though, if you can afford it, if you can go ahead and buy the TI Texas Instrument 84 graphing calculator, then it's a better calculator for this class, and it'll be the last calculator you have to buy. It's the one that all the colleges and SAT, ACT have decided this one does enough, but not too much. There are calculators out there that do more, but they do too much, and the colleges won't let you use them. So rather than spending $12, $15 on a calculator that then you won't be able to use later, if you go ahead and get that TI-84, the one colleges require, then you can go ahead and start learning it. It is not intuitive. It's old technology. It's not intuitive, but it's just the one that's agreed upon. You can use it on the SAT, the ACT, and in college. And also, if you take my math classes, I have, and you can do this without taking the math class, but I have videos in my Algebra 1 and Algebra 2 channels. I haven't organized it into channels yet, but I will, that are called calculator labs. And they teach you how to use that calculator, which is so valuable. So, sometimes we can't afford it. But if you can afford it right now, it would be good to go ahead and get that TI-84 graphing calculator and go ahead and start watching those videos with my math classes. If you're not taking the math classes, if you are taking the math classes, you'll get the calculator labs. I'll assign them to you. And go ahead and start using it, and you can use it in all your science and math. And as you use it in science, then it will help that math stick a little bit better. Science reinforces math, and it helps you learn it better. So anyway, that's the calculator. Other than that, you need a ruler that is metric. It's got centimeters and millimeters on it, pencils, pens, a notebook. That's basically what you need for chemistry. We will be doing labs, and with the labs, then you'll have certain things you'll need. I'll usually tell you things you can substitute. I try to get it as cheap as possible. I'll tell you to go look through the trash, find a cardboard box, stuff like that too. I try to keep it cheap for you. So anyway, like, share, subscribe. I'm Miss Lisa. This is chemistry. Let's get started. So if you have your book, turn to page 3, and let's talk about what is chemistry. And chemistry is the study of the composition of substances and the changes they undergo. It's matter and how it interacts is the way I like to think of it. It's the stuff that makes stuff up. If you look on page 4, it talks about the different sections of chemistry. The big two are organic and inorganic. Organic is the study of the chemistry of life, and life is based around the chemical carbon. So organic chemistry is the study of carbon, and carbon compounds. Inorganic doesn't have carbon, but it's not that you don't study some more inorganic with organic too and how it reacts. So those are the big ones. There are some other things you might hear, like analytical chemistry. That's where you're analyzing things and seeing what they're composed of. Physical chemistry is talking about theories, experiments. But if you become a chem major, like I was, then you will take analytical, you will take physical chemistry. These will be classes you take. If you don't become a chemistry major, but you're some sort of science major, you'll probably take college chemistry 1 and 2, and then you'll take organic 1 and 2. And most people, even who are science majors, if they're not chemistry majors, they stop there. But if they're chemistry majors, you go on and take P-Chem and quant and all these other fun classes. Biochem is the biology chemistry, the chemistry of life, and you can major in just biochem, and then you would also take some of those more upper level classes. Chemistry is a great major. I just have to try to sell it a little bit. You can make very good money as a chemistry major, and it's interesting and fun. So what's not to love? Now, every science class, we start with talking about the scientific method. One of my sons complained about this. He says, it's just dumb, Mom. Why do we have to talk about it every class? We need to talk about one class, and then we don't have to talk about it ever again. It's wasting time. Well, guess what? We're going to waste time. I'm going to talk about it. Sorry, Eli. He's already had this class. I made him take it. That's how I got started doing the tutoring classes for homeschoolers, is once my homeschool kids got high school age, people had always asked me, please teach my kids science and math. And I would tutor one-on-one, but I wouldn't do the classes. But then when my kids reached high school level, I was like, well, if I'm teaching them, I can teach somebody else. Come on, y'all can come join the class. And so that's how I started doing the science and math classes, was just letting more people come to when I would be teaching my kids. And then, and that's what led to this. I'll tell you a little of the background. What really led to it was COVID. This is 2020, and in the spring, we got the coronavirus, and all of my face-to-face classes had to go distant. So I started having to record the videos to be able to teach the kids who were coming to my tutor classes. And if I'm going to record, and then in summer school, it's still everything's distance, and I was having to record all the math classes for summer school. And I thought, why record them over and over and over again like I have for years for the kids who are absent? Since all the kids are absent now, they're all distant, I'll just record the videos while I do summer school, and then I'll upload them. So it was just going to be math. And then people were like, no, please, we need your science classes too online. So I was like, okay, I'll do it. So where the math, I recorded it all this summer, but I'm going to release a little at a time through the year. As it becomes time, I think it'll be less confusing to people. Then for science, I'm going to record it through the year, because I spent hours and hours and hours this summer recording the math videos. I worked on it all day, every day. And instead of, I don't have that chunk of time anymore, so I'm going to just do it a little each weekend for the science. And hopefully I'll be able to do it faster by the way I've changed how I'm doing the videos for YouTube. So you don't need to know the technical stuff, but hopefully it's going to be faster, where it won't take all day, every day. I won't have time for that, but I'll be able to do it quicker through, especially if I get it where people subscribe enough that I can go live again, like how I used to on Facebook. It will take much less time because I can just teach, because I already know the stuff. And if I could just, boom, hit record, then it'll be way faster. All right, so let's go over the scientific method one more time. Turning your book, if you're following along, to page 6, and at the top of the page you see a little graphic with it. Now, if you are also taking my biology class, you'll notice these are different. And I said this in biology. I said real scientists don't go, I'm going to discover something today. What is the scientific method? Oh, step 1, state a problem or a question. Step 2, do some research. In reality, there are things in science that are discovered completely by accident. But still, the scientists do what I call, they have on their science goggles. They're not just protecting their eyes from splashes in chemistry, but they will look at the world through using observation, looking at the world, looking for discovery, having good observation. And even if it is something on accident, they don't just go, huh, isn't that interesting, and go on. They go, huh, isn't that interesting? Let's do some experiments and learn more. So it is just having that sense of inquiry, and also designing experiments where they are controlled, where you only manipulate one variable at a time, you only change one thing at a time, and you try to also have something that has nothing changed so you can compare it. So technically, if you look at the top of the page, you'll see it starts with observations on this one. Sometimes it's a problem. Then you can come up with an hypothesis, an idea about what it is, design an experiment, test it. It could lead to a conclusion. It could be that you need more experimentation. Also, at that time of observation, while you're thinking of your problem or your question, usually what you do is you research, because it could be that it's just something you thought, I wonder what that is. You go do the research and you find out, oh, this has already been discovered, and you learn about it, and that's all you have to do. And it could be that somebody has already done some research and you don't have to go back and start at square one. You can stand on the shoulders of giants. You can start where they quit and learn something beyond what they did. A lot of times you have to change your experiment. You go back and kind of retool it and figure it out. Now, notice in the top of the page it says, then leading to a theory. So I need to explain to you what a theory is in science and how it's different than common everyday language. In common everyday language, a theory is an idea. I used to have a fruitcake theory, which is that I don't like fruitcake. Not one bit. I've never had a fruitcake I liked. And so my theory was that nobody likes fruitcake. Fruitcake has lots of sugar and alcohol in it, which are preservatives, and that they made all the fruitcake that's ever been made somewhere around 1950. And ever since then, people have just been re-gifting it to each other because nobody likes fruitcake. Now, is that a scientific theory? No, absolutely not. It's just an idea, and probably not even a very good one. And but it's common everyday language. Oh, my theory about that is nobody likes it. Well, then, if it was a science, in science, it is different than that. Also, with my fruitcake theory, it's been proven false. While I was teaching one time, this girl said, Miss Blackburn, I love fruitcake, and you would too if you had my grandmama's. And so I thought she'd bring me some. She never did, so I still don't like fruitcake. But she disproved it. When you have a hypothesis and you find one thing that negates it, then it's probably negated. You might have to redo the experiment and make sure you did it right, and it really does negate it. But that one girl negated my theory because she was the one who liked fruitcake. Now, that's common language. That is not science. In science, a theory is true, and it is a model to explain what is true in the world. So generally true, and this is my example. In science, we have something called the atomic theory of matter, and it's that all matter is made out of atoms. And this was an idea that was proposed by John Dalton hundreds of years ago, and he said that the atom was indivisible. And the word atom actually means indivisible. You can say it in the pledge. One nation, under God, atom, for liberty and justice for all. Indivisible, for liberty and justice for all. So, but now we know that John Dalton wasn't exactly right. That the atom can be divided into protons, neutrons, electrons, even more subatomic particles like quarks and mesons and all that sort of stuff. So that part of it wasn't true, but it was true that things are made out of matter, and the atom is the smallest piece that has the characteristic of the element. So one atom of gold is gold colored, and it has the characteristics of gold. If you break it down into smaller pieces, protons, neutrons, electrons, they are indistinguishable. They're like the Lego bricks that everything is made out of. So that theory of atoms is true, but it's changing, and that's why it's a theory. Now, in science, we sometimes use the word theory with the everyday use. For it to be a true science theory, though, it must be testable. It must be able to have repeated experiments, many repeatable experiments that are observable. So there are things about the past where we will use the word theory, but until we can test it, until we can observe it, it's the common everyday use of the word theory. So just know that even among science, we will use the everyday use, but when we call something like the atomic theory of matter, it's not that it's not true. We have electron microscopes. We have seen atoms, and they are round like little billiard balls, just like John Dalton said they would be. It is true that things are made out of atoms, but it's also changing. There's things we don't know. Dark matter is one of them. If you follow science at all, they're chasing dark matter, and it's going to be the answer to everything, and it's going to help us overcome E equals mc squared and Einstein's theory of relativity and dark matter, and it's kind of gets funny that dark matter, the salvation of us all. So there are things that we still don't know about, and so it's changing. Now, what about laws? Laws, I'm not sure exactly how the book defines it, but this is what I find helps my students best understand the difference. So theories are true. Laws, when they're used the scientific way, where it is observable and testable, you have to be able to run tests on it. And then theories, the way you can kind of keep it straight is they're so true, they're math. The math theories, they usually have a formula and a constant associated with it. So they are so true, they're math. The theories are changing. The math, this stuff is constant. We might learn more about it, but this math part is the math that the universe works on. An example is gravity. It's the law. It's that there is an equation for gravity, and it has a constant. The acceleration due to gravity is 9.8 meters per second squared. And so it is so true that it is this math equation. So math is the language of creation. It is the base of how everything operates is math, and so I love math too as a math teacher. All right, so hopefully that helped. Read your book, and that'll be part of your homework. Now, properties of matter. So matter has two kinds of properties. There are physical properties and chemical properties. The physical properties are things you can observe without changing it into something else. So physical properties of water. It's a liquid at room temperature. It is clear and colorless. It has a certain specific heat. It has a certain mass that we can look at a physical property that it has, but to describe all water, it would maybe have a certain density, the grams per milliliter. If I am going too fast, don't panic. Just remember this, that the physical property of water is things that are, it's like, you can think of it like its physical appearance, and it is what it is without changing it to something else. The other thing is the chemical properties, and that's how it reacts. So a chemical property of water is it reacts with calcium to make a solution that is not acid, it's basic. So that would be a chemical property of water telling how it reacts. The physical properties, and once it reacts, it's not H2O anymore. It's going to be something different. So physical properties, it's still what it was. Its chemical formula does not change. So if we take water and we freeze it into ice, it's still H2O. If it's a liquid, it's H2O. If we boil it and make it into steam, it's still H2O. Those are all physical changes, and we can describe its physical properties. A chemical change is where it changes from one thing to another, and we can describe its chemical properties, how it reacts with something else. So hopefully that makes sense. Read it in your book. It's pretty good. Okay, next idea. We talked about physical changes already. So the next idea in your book is mixtures. So first of all, we will do chemical reactions. And an example of one you do already is cooking. Say you're making biscuits. We're in the South. We like biscuits. And no, they're not cookies if you're watching this in England. They're soft little pieces of bread. And to make the biscuits, you have flour and you have a fat. It could be butter or shortening or lard or lots of different fats. And you mix them together, and then you add milk and you pat them out into little circles and you cook them. Once you have cooked it, a chemical reaction has happened, and you cannot get back out or separate the flour, the fat, the milk back out of it again. It has been undergone a chemical reaction, and it is no longer the same chemical. So that is something that has undergone a chemical reaction. And the new thing, the biscuit, has different properties than the dough did. The dough, you don't want to eat that. That's going to make your stomach hurt. It's wet and soupy. It has a different flavor. It is very different than the product that was made after the chemical reaction. But with a mixture, it is where you mix things together. They do not undergo a chemical reaction, and they do not bond together. So in a mixture, you mix the stuff together, and it still retains the properties of the things mixed together. My favorite mixture that I like to talk about is chocolate milk. I have been a longtime fan of Nestle Quick, and I can vary the amount. My husband thinks it's good to get 1 tablespoon out, scrape it flat, and put it in your big glass of milk and stir it up. You can still taste the milk, and you can taste the chocolate. It's a mixture. It is not turning into a new chemical compound. I, on the other hand, think it takes at least 3, maybe 4 heaping spoonfuls of Quick, and that you stir it up. You can still taste the chocolate in the milk, and notice that the amounts can vary for a mixture. But if you're making a chemical reaction, the amounts are very specific. They don't vary. Now, I had just about given up my love of Nestle Quick chocolate milk because they had changed the recipe, and it tasted terrible. It had all these vitamins in it, and it tasted like you were drinking a chocolate vitamin. It was nasty. If I want to take vitamins, I want to take vitamins. And if I want to drink chocolate milk, I want to drink chocolate milk. I do not want to drink chocolate vitamin milk. So I contacted the company on Twitter. I wrote them a letter. I have tried to reach out to them many times and tell them to please get the vitamins out of the chocolate milk. I would like my vitamins and chocolate milk separate. You have ruined one of my favorite things in the world. And then, I think it was last week or maybe the week before, I took a survey. I told them in the survey, this is terrible. Get the vitamins out of the chocolate milk. And I went to the store, my boys actually went to the store like 2 weeks ago, and it's back. It says Nesquik Classic, and it does not have vitamins in it, and it tastes like it did back in the 70s. I am so happy. My favorite mixture is back. So, mixtures, no chemical bonds between them. They retain the properties of their components, and the amounts can vary that you put in there. It's not set. If a mixture is the same throughout, it is homogeneous. Homo means same, genus, throughout. So it is the same throughout if it is homogeneous. My husband's chocolate milk is homogeneous. Mine, however, is not. Mine is heterogeneous. Hetero means different. And I don't overly stir mine, so I get the nice dark chocolate milk that I drink, and on the bottom I have a nice little layer of thick chocolate sludge. My husband thinks it's morally wrong that I do this, but I don't think so. I think it's delicious. That's the part, that's your dessert chocolate milk that you eat with a spoon, that thick chocolate sludge at the bottom. So his is homogeneous, mine is heterogeneous. And you're used to that word homogeneous with milk, aren't you? Because milk is the same throughout. If you buy it at the grocery store, if you go to the farm and buy it, it's not homogeneous. It has a layer of cream on top, and then it's the same underneath that. It has layers. Italian salad dressing is not the same if it's the kind you have to shake before you pour it on. It has layers, oil layer and a vinegar layer. All right, so the different layers are called phases. The part that has uniform composition. A solution is a homogeneous mixture where it's usually, you can think of it as that you can see through it. So this is Kool-Aid. Regular Kool-Aid, where you buy the little pack and you put the sugar in and you stir, and you hold it up to the light, and it's the same from the top to the bottom, and you can see through it. It has no layers, and you can look through your Kool-Aid and everything. If it's my favorite, black cherry, then everything looks dark red through your Kool-Aid. So think of Kool-Aid as a solution, chocolate milk as a mixture, my chocolate milk as heterogeneous, my husband's not so good, homogeneous. It doesn't have enough chocolate milk in it. One way to separate things in liquids is through distillation. You've heard of people in the years of Prohibition, when alcohol was not legal, then they would have stills. Still is short for distillation. And how you do it is different substances evaporate and condense at different temperatures. So they would have a mixture of corn mush that they would ferment, and then they would boil it, and the alcohol would boil off first. And then they would cool it down through copper pipes and recondense it, and what would come out the other end was liquor. It was white lightning, moonshine. And that was a big deal here in Georgia during Prohibition. It was probably a big deal everywhere. I think everywhere has stills, but there were a lot of them here in Georgia. And people trying to make their corn liquor and stay away from the revenuers who would catch you for doing the illegal thing of making moonshine. Now, in your book, they show what the kind of still, the distillation apparatus that we use in chemistry classes like. Some of them, there are variations on this. You can have a condensation tube that has beads in it too. So sometimes when you get to college, it might look a little different, but that is just a way of separating a mixture. We started with a mixture that had alcohol in it, but through the process you could get the alcohol off. I used to do a lab when I taught public school before, where it was called the foul water lab, and we had this really nasty water. It smelled terrible, and we would take it through different ways of separating this mixture. First we would filter it, and then we would try using the separation thing, and then we would distill it at the end. But we never got it pure enough that I would ever trust drinking it again. I mean, it was nasty. One time I had a girl throw up. She smelt it, went right over to the trash can and barfed. So it was something, the foul water lab. All right, if you turn the page to page 14, you will see the lab you're going to do. You are going to separate a mixture. The mixture is ink, and you're going to do it through paper chromatography, which means you're going to put water in the bottom of a cup. You're going to make a line on a piece of filter paper. It can be a coffee filter, it could be paper, and then you're going to suck the water through the paper, and it'll spread the ink out into the layers. So that's going to be your lab you're going to do this week. It's one that I did with my public school kids too, when I taught them. So elements and compounds, look on page 14. An element, where you find those, are on the periodic table, and I think it's in the back of your book. Oh, not in my book. Yes, it's in the back of your book. Turn to the very back of your book, and you can see the periodic table of the elements. Those are the smallest pieces of matter that retain the characteristics of the atom. There's 92 that are found naturally on Earth, the biggest one being uranium, which I always think of SpongeBob and Plankton with the friendship song, Uranium Bombs. Friends, F is for friends who do stuff together. Anyway, you'll have to look it up. I'm sure it's around. YouTube and Plankton singing the friendship song. Anyway, so those are the elements. When the elements get together, so like example one is hydrogen. Another one is oxygen. When they get together and form chemical bonds, they become a new substance. So hydrogen gas and oxygen gas can go together and make H2O, which is water. It has new properties once it forms those bonds. It's not a mixture, it's a chemical compound. So elements is just one thing. Compounds or two or more. It can have lots of different kinds of atoms in it. All right, so read through your book. Hopefully it'll make sense. The symbols are the letters on the periodic table. They're either one capital letter or a capital letter and a lowercase letter. It is not a lowercase letter written big. It's not a capital letter written small. It is exactly a capital letter or a capital letter and a lowercase letter. This is because of communication. Scientists all over the world have agreed on this way of writing chemistry. And like my oldest son, Nathan, is in the doctorate program at Tech for a chemistry. He was a chemistry major. And he goes online and he watches videos from around the world, China, India, and they will be speaking a different language. But he understands what they are writing on the board because they are writing in element symbols, and he can read those symbols and he can see the math. The numbers are written the same way, and he can know exactly what they're doing even though he doesn't understand their language. And he learns by watching whatever this person is explaining across the world, because we all agree in all the countries on the periodic table. It is our means of communication and our symbolism that we use so we can communicate as scientists. Okay. All right. So you can see some of those symbols and a little bit about the history of the symbols in your book on page 16 and 17. Page 18, it talks about chemical reactions. So I've got one here for you to look at on my little board. Got my big board behind me. But here we have, on this side, you write the ingredients. But we don't want to call them ingredients in chemistry because somebody might think it's okay to eat them, and it's not. So we call them the reactants. So it's a recipe for chemistry. And this is the recipe for water. You can take hydrogen gas and oxygen gas and shock it with electricity. And the arrow, this is what you put in. The arrow shows you then what you get out. So this is in, that's out. These are called the reactants. Those are called the products. They're what you produce. And the condition of the reaction is often written on top of the arrow. And my condition here is electricity. I'm going to take these two gases, shock them, and it will make liquid water. Now, there's a thing with these numbers underneath. There's a law in science, and it's called the law of conservation. It's the law of conservation of mass and energy. And it says that all the matter, all the mass, and all the energy that is here has been here since creation. And ever since then, it just gets recycled. So like the matter that makes up you came from your food. Those atoms have been around since creation, and they just change forms from one to another. So another way of thinking this is you cannot create or destroy matter. You can only change it from one form to another. So in our chemical equation, we had 4.8 grams of hydrogen gas, 38.4 grams of oxygen gas, and when they reacted, they made 43.2 grams of water. If you add it up, you'll see it's the same, because we cannot create or destroy mass. Now, this is a recipe, and it's not really correct right now, because later on we're going to learn something called balancing a chemical reaction, which will tell us the amounts. So this is like my recipe I told you for biscuits, that's flour and fat and milk, but I didn't tell you how much. That's what this is. This is a recipe for water without me telling you how much, because it's a whole other thing. You're not ready for it yet, but you will be. We'll do it this year. Don't worry, you'll get there. All right, so the law of conservation of mass, it's also energy too, was on page 19. All right, so read through all of this. I will assign you some homework in the description. Do your homework. You moms, remember there are tests with answers on the Facebook group, Mrs. Lisa, and you can join that. Kids, you can't, because there are tests with answers on the group, and that's on Facebook. So come back next week and we will learn some more science. I'm always going to leave you with one of my catchphrases, which is, science is great.